Okay, now that we've got graph implementations and a way to actually represent a graph in computers, let's talk about things we can do with the graphs. So we're going to start with something called breadth first search, abbreviated BFS. So this is a graph traversal. It's going to explore the graph starting at a particular node. So the basic idea is that we start at some particular vertex or node. We're going to visit every place that's adjacent to it, and then we're going to visit every new place that's adjacent to the places from the previous step, and so on and so forth. We'll continually expand out, visiting new as yet unvisited nodes until we've reached everything that's accessible from the original start node. Okay, so I want to take a quick look at breadth first search's algorithm. So this is a Wikipedia page which gives one particular version of breadth first search. Notice they give an example here that looks a lot like the binary trees that we've already spent some time exploring. And also it describes a couple of different things about the time complexity and space complexity of this particular algorithm. So let's focus on the algorithm itself. So breadth first search, we'll search a graph G, and it's going to start at some particular start or root node. It's going to use a queue, so again, we're reusing some of our data structures from earlier in this semester. It's going to label the root or that start node as being discovered. So we need some way of kind of marking off nodes to indicate that we've already visited them. It'll add that root node to the queue, and then it's going to continue doing stuff until the queue is empty. So it'll grab the thing at the front of the queue. If it's not some sort of goal, and we're going to ignore that for now, it will look at all of the edges from that node to other nodes. It will check and see whether the destination has already been visited or not. If it's already visited, we don't want to visit again, so it's not interesting. But if it's not visited, we'll mark it as discovered. So if it's not new, we'll mark it as being already seen at this point, and we'll add it to our queue. Okay, so I want to go through a basic example of this with a simple graph. Okay, for my example problem, I've got a simple undirected graph. So notice that it's got all these nodes over here and these two over here, H and I. So if you remember, our algorithm starts off with some sort of a queue. I'm going to choose to start from node A, so I'm just going to go ahead and indicate that with a little arrow here. And the first thing our algorithm does is it marks that start node as being discovered already. So I'm going to kind of cross out the nodes that I've already discovered, and it adds it to our queue. Okay, so that's the first couple of lines of our algorithm, and then we get into the loop of the algorithm. It's going to continue looping until this queue is empty. So it starts by removing an item from the queue. So I'm going to continue to leave the items in the queue here, and I'm going to just kind of move from left to right and kind of cross out items that we'd think of as being removed from the queue. Okay, so we'll dequeue the first item in our queue A. Then we're going to look at everything that it's connected to. And we're going to see that it's connected to D, and D has not yet been crossed out, so we will both cross out D, and we will add it to our queue. A is also connected to C. It hasn't been visited, so we'll cross it out and add it to our queue. A is also connected to B. It hasn't yet been visited, so we'll cross it out and add it to our queue. Okay. Okay, so now we're kind of done with A, so it's going to be removed from our queue, and again I'm going to kind of indicate that by lightly crossing things off. And then we move on to the next item in our queue. So A has been dequeued, we're up to D. We repeat the same process. We look at everything D is connected to. So D is connected to A, but it's already been discovered. It's not interesting. D is connected to F. It hasn't been discovered yet, so we're going to go ahead and both mark it as being discovered and adding it to our queue. D is connected to C, but it's already been discovered. Okay, so that's it. We're done with D. I'm going to kind of lightly cross it out as well. We move on to the next item in our queue, C. We're going to repeat the process. We're going to look at everything that C is connected to. A has already been discovered. D has already been discovered. Nothing to do there. Okay, we again remove it from our queue. Move on to our next item, B. So same process. B is already it's connected to A. It's already been discovered. B is also connected to E, which hasn't been discovered yet. So we mark it as discovered and add it to our queue. Okay, and now we're done with B. It's removed from our queue. Next we visit F. Same process. D has already been discovered. G has not been discovered, so mark it as discovered, and add it to our queue. Okay, and then we continue the process. F gets removed from our queue. E, everything around it we've already discovered, gets removed from our queue. G, also everything's already been discovered and is removed from our queue. Okay, so I want to take a look at the list of stuff that's been generated here. So as we were processing things, the basic order we went through things were A, D, C, B, F, E, and G. So some of these choices were arbitrary. When I went from A to D, that was just kind of an arbitrary choice. I could have gone from A to C or A to B. They're all one step away. They're all adjacent to A. I'm going to kind of draw dividers here. Basically what we did is we kind of divided this up in steps, things that are 0 away from node A, and then the things that are basically 1 link away from node A, and then F and E were 2 links away from node A, and G is a total of 3 steps away from A. And we saw that we never visited H and I because they're not connected. So this algorithm is useful for a couple of different things. One of the things is we can discover the minimum distance to get to a particular location from a start location. Another thing we can do is we can use this to determine the set of connected components. So this is one set of components that are connected together. And we could run this on each individual vertex that hasn't yet been discovered. And so we could run this again on either H and I, and it would kind of identify this as a set of things that are connected together. So sometimes that's useful. So like in a social network graph, you could kind of identify distinct social groups that are kind of isolated. They're interactions within the group, but not between one group and another. Okay, so let's go back to the Wikipedia article here and do kind of a quick analysis of how much time this is going to take and also how much space it may use. Okay, so we have to make some assumptions since this is just pseudocode. We have to decide which implementation of the graph we're using. I'm going to go ahead and use the adjacency list implementation. So this is kind of crawling through the graph one node at a time, and it needs to expand and find the adjacent nodes. So that's partly why I choose the adjacency list, because it is very good at that operation. So this is using a queue. I'm going to assume the queue is based on a linked list where we can easily add to the end of the linked list in constant time and remove the beginning in constant time. So creating the queue I'll assume is a constant time operation. Labeling the root is discovered. I'm going to guess that our vertexes have an instance variable, a property that indicates whether they're discovered or not, a simple Boolean. And we can call a setter in constant time. Adding something to the back of the queue with a linked list would be constant time. So all that setup stuff I'm going to assume is constant time stuff. Next, we've got this while loop that's going to iterate until the queue is empty. So if you remember, each node is only added to this queue if it hasn't already been visited. So that means that each node will only be added once. So the total number of iterations that this loop could execute will be based on the number of vertices we have. Each vertex can be processed at most once. Okay, so now I'm going to focus on the body of this. So dequeuing something from a linked list would be constant time. I'm again going to ignore this idea of getting to a goal. I'm just going to not focus on that for the time being. It would make our algorithm end early. It doesn't really make our runtime any worse. Okay, the next part of this is about finding edges from a particular vertex. We process each vertex once, okay, at most once. So the total number of edges we may get would basically be twice the number of edges in the graph. We may see an edge from each vertex on either side of the edge. So the total number of times that the stuff in here may execute would be proportional to the number of edges that we have. Okay. Okay, so if something on the opposite side of an edge hasn't already been marked, we label it as discovered, and then we enqueue it. By the way, just to back up, when I say this is the total number of edges, that's actually over the entire execution of this. It's not the total number of edges for each vertex. We're going to process each edge a total of 2 times over the entire execution of the outer while loop. Okay, so that's really important. So our outer while loop may take v steps, and the inner for loop in total will basically be based on the number of edges. So our total execution time is somehow based on the sum of the vertices and the sum of the number of edges. While we're here, I also want to take a look at the example that they use in the Wikipedia article. So they've got kind of two variations on this. One of them, they draw the graph almost in a tree-like way. So I'm going to go ahead and zoom in on this. So it starts at A, and they're kind of highlighting the things that have been added to the queue versus the things that are actually visited. So this is called a breadth-first search, partly because it's expanding out as widely as possible before it goes a little bit farther away from the start node. So we get A, their start node, then we get all the things that are one step away from A, and then we get all the things that are 2 steps away from A, and then all the things that are 3 steps away from A. So that's especially clear in graphs like this that look somewhat like a tree.